Hi, and welcome to another Hopper on 6502 video. This one's part of the 65 Uinu playlist. As I mentioned in the previous video, I'll show you how to get your first program up and running on this device. So let's get cracking. Okay, let's start off by seeing what the minimum code is that's generated by this toolchain. So this is the Hopper development environment. Typically, you go and set your options up, run the optimizer, run the disassembler, save on build. Very Pascal-like. This is the same preprocessor as Hopper, so it has all the features of Hopper. You have to tell it which device you're targeting, and if you do that, it'll put the correct preamble code in. You can have an anonymous main method like this, and there's your loop forever loop. You don't need to worry about the syntax right now. I just want to show you what code it generates. So if I build this, at the bottom of the screen, we see, that it's been through the entire process, including generating our assembler. So now we can go look at what code that generated. So we'll load up. I know that in the debug folder, there should be a listing. And there it is. So this is the code that was generated by the assembler for doing nothing. Here's the doing nothing part. It's just jumping around in the loop. But before it even got there, it did some preamble code that it's going to put into all 65 Uinu programs. And this is Anders Nielsen's code. So clear the decimal flags so we're not in binary coded decimal mode by mistake. Most 6502 programmers put this at the beginning. We're also turning off the interrupts, disabling interrupts. So NMI and IRQ. Because it is a MOS 6502 chip, strictly speaking, it should be impossible to generate these interrupts because there's no IRQ pin and there's no NMI pin and there's no break instruction because it's not the Western Design Center instruction set, it's the MOS instruction set. But just to be safe, we're putting in a disable interrupts. Then this is Niels divided the 0 page so that the bottom half, 0 to 127, is the RAM on the Riot chip. And then he's got the Riot chip itself at 80 hex onwards. So he sets up the stack pointer to be at the top of that RAM range of our 128 bytes of precious RAM. And then he uses this loop here to clear that 128 bytes to 0, which is, it's nice to start with default zeros so that your program always starts the same way and is predictable. You don't have electrical noise in your 0 page to give you an unpredictable program. So this is what is the minimum code generated by the assembler. Okay. I quickly crafted this little demo. I can get rid of that. So what does this do? You can use that hopper there. This is optional. You can either have an anonymous main like that, or you could call it like that so that you know where your main is. It helps to find it if it's a bigger program and you want to know where's my curly brace that marks the beginning of my main program. This program is going to use two features on the device. So you've got a user button there, and you've got a little green built-in LED there. And the user button is on port B pin 6, port B bit 6, and the LED is on port B pin 7. So I'm demonstrating how to use the if, how to use the loop, how to do method calls. I'm demonstrating how you qualify namespaces. So I've got this unit here, so there's programs, and if I right click on this, there's a unit. So these are Anders's definitions for his Riot registers. A lowercase first character means private, an uppercase first character means public. That's similar to the Go language from Google. And then you can qualify them with the unit's name also doubles as a namespace name, so you can qualify them like this with a dot. And that allows you to start building big projects and not have conflicts if the same name is used in two different units. Like there's really common names that get used all the time, like delay or print or whatever. Anyway, delay long is from Anders's code. So I've got a utilities unit where it uses the timer to do a delay. So I'm setting that up, and here I've qualified it, and here I haven't. So I could do either way works. You don't, if there's no ambiguity, you don't need to qualify them with the namespace. And here's my calculation to get from you know, the number of ticks to the number of milliseconds. So I get close enough to 500 milliseconds, and that's 488. So I have to call it twice since we've only got a byte, and that's how I get my 500 millisecond delay. All right, what are we doing here? First thing we do when we start up is initialize the data direction registers of the Riot chip, and you set them to zeros to make them all inputs, which is the safer thing to do than to, you know, punch out voltage on them, especially when we don't have that much in the way of, anyway, safe to put them as inputs first, with the exception of bit 7, which is the LED, which is going to be an output, and that's on the register B, and that's register A. And then we set register B's values to all zeros, which these don't really matter because they're inputs, but that sets the LED to a 0, and 0 is on for the LED, and 1 is off for the LED. Okay. Now, how does our loop work? In our loop, we're using the bit instruction, and I should show you about that. Let's switch to my desktop to... I'll put a link to this reference, and I'm looking at the MOS instruction set here, MOS 6502 instruction set, and here's the bit instruction. So it ANDs the accumulator with the memory address, which in our case is a 0-page address, and then it'll set the negative flag, which is a sign bit, or the overflow bit based on the values of bit 7 and bit 6 in the memory address, which is our 0-page address. And it doesn't, it also sets the zero flag, but we won't worry about that. And it doesn't change anything else, so it doesn't change the accumulator. Right, so let's switch back and see how we're using that. So we do the bit instruction on that 0-page address, which is the B register, and if this bit 6 is set, that will be the button, right? But it's actually, again, reverse logic. So if it's not set, if it's 0, it means the button is being pressed. So if the overflow flag is not set, then we want to go in here and we want to put the green light on. If not, we just skip past here and we keep it off. We just keep running. So it should go on, when the button's down, it should go on for 500 milliseconds and then off for 500 milliseconds. So this program is demonstrating the use of the button, the use of the green LED, and also the use of the timer in the Riot. Right, so let's build. So I've built, and I've got an Intel hex file as the output. So let's switch back to our full screen. And I'm using quite a common EEPROM burner. And I have quite a common EEPROM burner here. So let's find our hex file, our Intel hex file. It's going to be in the bin folder under the hopper folder, and we're going to load up that Intel hex file. And I still have to put the origin in here. I haven't fixed that yet. And then we burn our EEPROM. And that was pretty quick. So we can now take our EEPROM and put it in our device. Make sure the power is off. It's unplugged. And let's pop that in there. Okay. Turn the power on. And we get some little LEDs lighting up, but nothing exciting happening yet until I press the button. And once I press the button, can we see that? It's kind of hard to see. There we go. Hard to see on camera. You can see the little green light flashing. So when the button's down, the green light's flashing as we expected. And as I release it, it stops flashing. And as I put it down, it starts flashing. There we go. So in a nutshell, that's how you get your first program up and running on your 6.5 Arduino with the Hopper 6502 assembly toolchain. Thank you for watching. I'm going to follow up with some more detailed videos about the 6502 assembler, the Hopper 6502 assembler. There'll be two videos. The one will explain the features of the assembler, and the second one will look under the hood at how the optimizer works and how it saves you having to make the sort of optimizations we usually do by hand.